So welcome to Genique. Today here, we are giving you the quick revision video, okay, final revision video for the electromagnetic theory. So here, for revising the entire subject, so these are the what is the visible on the board. It is very important for you, okay. So that's why you have to focus on this entire what I have given. So there will be the maximum 4 to 5 hours of revision video will be there. So you have to focus on this revision video so that you can get a good amount of marks in your GATE examination and also in the engineering services examinations. Okay. So here, for getting into this revision video, first of all we should know how the electric fields and magnetic fields are generated. So what is the basic cause of these electric fields? Okay. So even you didn't study till now also, and it will be helpful for you. So just keep concentrated, okay, so that you can get good amount of marks in your examination. So it will help you in your examination and also, okay. See, observe this. So what are the causes of electric fields? So what is the cause of electric field and magnetic field? We know the basic cause of electric and magnetic field is a charge only. So depending on the state of the charge, the electric field is generated and magnetic field is generated, and also electromagnetic field is generated. Electromagnetic wave is generated. Okay. Suppose if the charge is at a stationary point, if the charge is at any point which is stationary, okay, which is an independent of time, then there exists the electric field. Okay, the electric flux lines are straight lines. We know this. Okay, suppose if the same charge is moving in a conductor, so then constant. Okay, if the charge is moving with a constant velocity, that means the DC current. So if there exists a DC current, there exists the magnetic field. How the magnetic field exists? The magnetic field exists around the cause, means around the current carrying conductor. Okay, so by these 2 points we came to know that the electric flux lines are straight lines and the magnetic flux lines are the circles. So this is the point you should understand. So how the electromagnetic wave is generated means, suppose if we take the same amount of charge, if it is varying with respect to time. So if the charge is varying with respect to time means the current is varying with respect to time, right? So that is what? That is an AC current, alternating current. So if there exists an alternating current, so there will be the formation of the electric field and the magnetic field. Okay, the electric field is a function of time and the magnetic field is also a function of time, and they will be generated simultaneously. So that is the point you have to understand. Okay, so if it is clear now. So we came to know that the electric field is generated because of the stationary point charge and the magnetic field is generated because of the stationary current, okay, means DC current, okay, and the electromagnetic wave is generated because of the alternating current, right? So apart from this, is there any other causes of electric and magnetic fields? We have to know. Yes, there are some other causes of electric field and magnetic field. Okay, so we will discuss how the electromagnetic waves are generated in the next video, but now focus on how the electric and magnetic fields are generated, right? See, we came to know that if there is a point charge, due to that point charge, the electric field is generated, right? Suppose not only that point charge is generating electric field, but also some other geometries are there, some special geometries are there. So those geometries are, okay, this is what? Rho L, Rho S, Rho V. Rho L is the line charge, Rho S is the sheet charge, Rho V is the volume charge density, okay, volume charge. So the units of each and every parameter is important. The units of each and every geometry is important. Okay, what are the units of this Q? Q means a point charge, okay, the units are the coulombs. Line charge, the Q is distributed along the length of the line, so that's why Rho L is line charge. So Coulomb per meter. For this Rho S, if the same amount of charge is distributed over the area, then it is sheet charge. Okay, suppose if the same amount of charge is distributed over the volume, that is called as the volume charge. So the units are coulombs. Coulomb per meter, Coulomb per meter square, Coulomb per meter cube. These are the very important parameters and also the units. Okay. So next one is, so what are the causes of H field? We know due to the current carrying wire, the magnetic field is generated. So not only the long length current carrying wire is generating the magnetic field, okay, but also a small length current carrying wire also can generate the magnetic field. What is the small length current carrying wire? It is represented with IDL. So it is called as the point current element. It is called as point current element. So it is point current element means what? It is just like a point only, but it is a wire. It is just like a point, but it is a wire. So this point current element is similar to this. This point current element is similar to this. The length of this one and the length of this one are same. Just a point where DL tends to 0, right? And we know a current carrying wire is generating the magnetic field, right? And also if the same amount of current is passing through a sheet of length L, okay, then we name this one as a K, okay, it is called as the sheet current. Suppose if the same amount of current I is passing through a solid conductor, okay, we name this one as current per cross sectional area. So that's why we call this one as J. Okay, so all these four will give you the magnetic field. Okay, what are the units? We know the units of this I are amps, right? The units of I into DL is ampere meter. Okay, so this is what it is, a sheet current. Sheet current is nothing but the current per the unit length. It is called as ampere per meter square. Okay, units are ampere meter, ampere per meter, ampere per meter square. So these are the units you should understand. Okay, so we came to know that because of these all special geometries, we came to know that electric and magnetic field are generated. So how to measure those fields? To measure those fields, so we use 4 vector quantities here. So what are the 4 vector quantities? The 4 vector quantities are EHBD. EHBD. So E, we know electric field intensity vector, H is the magnetic field intensity vector, B is the magnetic flux density vector, D is the electric flux density vector. These all are vectors you should understand. Okay, these all are vector quantities. And the units of this one, electric field, we know volt per meter, ampere per meter, Weber per meter square, Coulomb per meter square, right? So these are the important parameters and units of this. Okay, the measure of field strength at any point can be expressed in terms of the electric and magnetic fields, EHBDs. Okay, so you can represent in any of the way. Okay, so now after completion of this, so we should focus on the very important parameter without which there is no the concept of the electromagnetic theory, there is no analysis of the electromagnetic theory. So the important parameter in this subject is the del operator. Okay, so without this operator there is no possibility of analyzing the subject. You should understand this. So based on this you will get the questions. So you have to be very careful while operating with the del. Okay, so first of all we should know what is a del. So del is nothing but it is a vector operator. First of all you should understand that it is a vector operator. So del is defined as dou by dou x of something into ax, dou by dou y of something into ay plus dou by dou z of something into az. It is a vector operator. So what are these ax, ay, az? Ax, ay, az are the vector operators. Ax, ay, az are the unit vectors along x direction, along y direction, along z direction. So we came to know that this del operator is a vector operator. That is the point you have to understand. In general, the del operator is defined only in the Cartesian coordinates. Okay, del operator is only defined in the Cartesian coordinates only, but we extended it to the spherical and cylindrical coordinates also. Okay, so that is the point. You have to mathematically it is given for the Cartesian coordinates only. Okay, but you cannot write in this form for the cylindrical and spherical coordinates. That is the point you have to understand. Suppose if I want to use the spherical coordinates here, I cannot write dou by dou rho of something into a rho dou by dou phi of something into a phi, dou by dou z of something into az. I cannot write like that. Okay, it is only valid for the Cartesian coordinates only. And we will come to know how to write the del operator for the cylindrical coordinates and spherical coordinates. Okay, so there are some special vector identities are there, so you should remember these vector identities forever. Okay, if you know the del operator expression, you have to remember these three vector identities. They are very, very important. So what is this del cross del f is equals to 0. So what is the meaning of this? The curl of the gradient. Already you know del cross represents a curl. So del of any scalar is represented gradient. Okay, so del cross gradient, del cross of this gradient. The meaning of this one is what? The curl of gradient is 0. The curl of gradient is 0, right? And also the divergence of the curl is 0. The divergence of the curl is 0. And one more important vector identity is del cross A is equals to del of del dot A minus del square A. So these are the very important vector identities you have to understand and you have to remember this. Okay, and next one is, suppose if you take any vector, so this vector may be in terms of the Cartesian coordinates, or it may be expressed in terms of the cylindrical coordinates, it may be expressed in terms of the spherical coordinates. Okay, so I am writing a generalized vector here. Let us suppose a bar is maybe in vector Cartesian coordinates, cylindrical coordinates, or the spherical coordinates. So I am naming this one as AU, AV, AW. Okay, so you can represent this one as a bar is equals to AX, where AU, small AV, small AW are the unit vectors along the UVW directions, right? UVW directions. So here AU representing the scalar quantity or the component along the AU direction. Okay, AV represent the component along the AV direction. AW representing the component along the AW direction. Okay, suppose if you want to represent this function in terms of the Cartesian coordinates AX, AY, AZ. Suppose if you want to represent this function, this vector in terms of the cylindrical coordinates arrow, A5, AZ. Right? Suppose if you want to represent this function in terms of the spherical coordinates AR, A5. So first of all you should know what are the coordinates. The cylindrical coordinates, the Cartesian coordinates, cylindrical coordinates and spherical coordinates. Okay. So up to the Cartesian coordinates we are comfortable. Up to the Cartesian coordinates we are comfortable. But what if you go for the cylindrical coordinates, if you go for the spherical coordinates, that is a challenge. So we can define the del operator for the Cartesian coordinates. So up to there we are okay. But what if I want to go for the spherical and cylindrical coordinates, we should concentrate that. Okay. So for that we have to concentrate on this table. Okay. This table will help you ever. Okay, so whenever you are dealing with the electromagnetic theory, antennas or waveguides or microwaves, okay, so this table is very, very important for you because mainly we are using the three types of coordinate systems. Okay, so those are Cartesian coordinate system, cylindrical coordinate system and spherical coordinate system. So I am writing a generalized formula for divergence, curl and gradient. It is called as the divergence. This is called as what? It is a curl. It is a gradient. It is a gradient. What is this? It is called as the divergence. It is called as the divergence. Okay. So the defining the divergence, curl and gradient are very easy for the Cartesian coordinate, but it will be very difficult for me, okay, to define the divergence, curl and gradient in other coordinate systems like the cylindrical coordinate system and spherical coordinate system. So that's why we are writing we are using this generalized formula for divergence, curl and gradient, and also the Laplacian operator also. Okay, so we should know that the del operator can be operated on a vector, scalar and on itself also. Okay, suppose the del operator is operated on a vector, so it can be in the form of a divergence, it can be in the form of a curl. Okay, and suppose if the del operator is operated on itself, then that will become Laplacian operator. Okay, suppose if the del operator is operated on the scalar, it is called as the gradient operation. Okay, so this is del dot A. This del dot A representing the divergence of the vector. So what are these H1, H2, H3? So these are the scaling parameters. Okay, suppose if you observe this, so these are the Cartesian coordinates, cylindrical coordinates and spherical coordinates. Okay, so for this, the scaling parameters are, okay, for this I am representing this one as U, V, W in a generalized way. I am representing these all parameters are U, V, W. Okay, U, V, W. Suppose if you take the Cartesian coordinates, in the place of U you have to write X, in the place of V you have to write Y, in the place of W you have to write Z. Okay, so in the place of H1, if you take the Cartesian coordinates, it is 1. In the place of H2 you have to write 1. In the place of H3 you have to write 1. Suppose if you go for the cylindrical coordinates, wherever there is a U in the generalized formula, you have to write U. You have to in the form of in the place of V you have to write phi, in the place of W you have to write Z. Okay, similar to in the place of U for the cylindrical coordinate system you have to write R, in the place of V you have to write theta, in the place of W you have to write phi. Okay, and there will be a confusion that, okay, how to identify the R, theta, phi. Okay, you know, suppose if you go to the crash course of the EMTs, so there will be there is a video on the cylindrical and spherical coordinate systems in detail, so you can identify the rho, phi, z, r, theta, phi. Okay, so you can go to that video and you can watch it. Okay, so now what are the ranges of this x, y, z? Ranges of these parameters. The range of these parameters are x, y, z are minus infinity to plus infinity. Okay, suppose if you want to know the range of this rho and r is 0 to infinity. 0 to infinity. So this is the range of rho and r, right? So what are the range of this phi and theta? Theta is having 0 to pi. You have to focus on this. Okay, theta is having a range of 0 to pi and phi is having the range 0 to 2 pi. Okay, so this theta is called as the elevation angle and phi is called as the azimuthal angle. Okay, phi is called as the azimuthal angle. So why we are using these coordinate systems? We are using the coordinate system to identify, to represent a point with respect to a known reference. So to identify that point, we should know all this x, y, z, rho, phi, x, y, z, rho, phi, z, r, theta, pi. Okay, so while we are dealing with the different types of coordinate systems, you have to remember this table. Okay, you have to remember this table. Suppose if you come to this divergence operation, suppose if I want to write in terms of the Cartesian coordinates, the divergence operation del dot A is equals to 1 divided by H1, H2, H3, 1 divided by 1 into 1 into 1, 1 dou by dou x of H2, H3, 1 dou by dou x of Ax, right? Dou by dou y of Ay, dou by dou z of Az, right? So I can write like this. Suppose if you want to write the divergence operation in cylindrical coordinates, so what I have to write? 1 divided by H1, H2, H3. H1, H2, H3 means 1 into 1, rho into 1 means rho. So 1 divided by rho into dou by dou rho of H2, H3. H2, H3 is how much? Rho into 1. So dou by dou rho into a rho plus dou by dou phi of, in the place of phi I have to write pi, dou by dou pi of H1 H3. H1 H3 is 1 into 1. 1 only. Okay. Dou by dou phi of A phi. Right. Suppose if you want to for this dou by dou z of H1 H2. H1 H2 is means what? 1 into rho into Az. Okay. Similarly, I can also write this divergence operation for the spherical coordinate systems also. So here there is a curl operation. So I can use this generalized formula for all the three coordinate systems. Okay. So here also it is given the gradient operation for the scalar. Always remember the gradient operation is only operated on the scalar only. So the gradient is not applicable for the vectors. Okay. The gradient is only operated on the scalars. That is the thing you have to understand. Okay. But what is the result of this gradient? The result of this gradient is a vector. It is a vector quantity. Okay. Always the gradient operation is operated on a scalar, but the resultant is a vector. And also here it is what? It is a Laplacian operator. The resultant of this Laplacian operator can be operated on vector and scalar. Okay. But the resultant will give you the scalar only, because what is this? It is a vector operator. The dot product of this vector will give you scalar. You have to understand that. Okay. The dot product of, see, observe this, the divergence operation. The resultant of the divergence operation is a scalar. Okay. Because vector into vector dot product vector gives you a scalar. Here it is a vector, cross product always gives a vector. The results you have to know, right? It is a scalar. The gradient of the scalar will give you vector. Okay, it is a vector and it is a vector. Okay, the dot product of two vectors is a scalar operation. Okay, it is a scalar. You have to understand this. Now, so after finding the divergence, curl and gradient and Laplacian, okay, and there are very, very important concept. Next one is the differential length, surface area and volume. What is the differential length? What is the differential surface area and differential volume? So without these three concepts, there is no integration and there is no derivation for this. Okay. So you have to focus on this differential length, differential area and differential volume. Okay. Because always we will find the total effects. So total effects means we have to find the integrations, okay, with respect to length, with respect to surface area, with respect to volume. So to find the total effects in any region, we use the integration. Okay, we use the integration. Suppose if you want to find the effect at any point, we use the differentiation. Okay, so for that purpose we should know the differential length, differential volume, differential surface area. So for finding the total effects in any region, we should integrate the effect in a small area, so or a small length and a small volume. So to know this, we have to define the differential length, the differential surface area and differential volume. These are very, very important. Okay, so for differential length, surface area and volume also there is a generalized formula. Okay, so it can be, there may be, if the vector is in the form of Cartesian coordinates, you can write what? dl is equals to h1 is how much? 1 dx ax 1 into dy ay 1 into dz az. So you can write dl is equals to dx ax dy ay plus dz az. Okay, so that means what? You can easily write the differential length in terms of the Cartesian coordinates, but it is very difficult for you to calculate the differential length in terms of the cylindrical coordinates and the spherical coordinates. So that's why you have to use this relation. It is generalized formula. Okay, suppose if you want to write the difference length in terms of the cylindrical spherical coordinates, suppose if I want to write this differential length in spherical coordinates, I have to write, what is this? h1 in the spherical coordinates is 1 dr ar plus h2 is r d theta a theta plus h3 is r sin theta d phi a phi. Right? What is this? dr ar dRAR, r d theta a theta, r sin theta d phi a phi. Right? So like this, you can find the differential length in any coordinate system. So it will be very helpful. Suppose if you are following the graphical approach, okay, and then some other techniques are also there, but it is a very effective method and it will be very useful. So in finding the answers, okay, in a limited amount of time. So it will be very useful. So you have to focus on this generalized formula and this table. If you know this table and if you remember some 5 to 6 expressions, and it will be very helpful for you in answering the questions and also analyzing the subject also, it is very useful. Okay, so don't ignore this. Suppose if you want to write the differential surface area, the differential surface area is given in this form. Okay, the differential surface area H2 H3 dV dW AU H1 H3 du dW AV plus H1 H2 du dV AW. Okay, AW. So we should know that this differential length is a vector quantity because I am writing AU, AV, AW is a vector, right? So it is the component in the direction of AU, it is the component in the direction of AV, it is the component in the direction of AW, right? You should remember that it is a vector quantity and surface is also a vector quantity and the surface is also vector quantity. So what is the meaning of this one? What is the meaning of this one? So it is the surface area in the direction of AU. It is the surface area in the direction of AV. It is a surface area in the direction of AW. Right? It is a surface area in the direction of AU. It is a surface area in the direction of AV. It is a surface area in the direction of AW. Suppose if I want to write the surface area in Cartesian coordinates. Okay, so how can I write the Cartesian coordinates? How can I write the differential surface area in the direction of AX? In the direction of AX, how can I write? H2 H3. H2 H3 is 1 into 1 only. This is d by dz. So d by dz AX, it is dx dz AY, it is dx dy AZ. Okay, so like this you can identify you can write the differential surface area. Okay, similarly if you want to write, so this is also what? It is a vector quantity. Always remember the surface is a vector quantity. It has a direction. Definitely it has a direction. Okay, so this surface area is having 3 components. Okay, so this component is this blue pen represents, observe this blue pen represents the surface area in the direction of AU. This is the surface area in the direction of AV. This is the surface area in the direction of AW. Right? So this is dV. dV means what? dV means H1, H2, H3, du, dV, dW. So it is also applicable for all 3 coordinate systems. Okay, suppose if I want to write the differential volume in spherical coordinate system, first of all I have to multiply H1, H2, H3. H1, H2, H3 is 1 r sin theta. So r square sin theta into dr d theta d phi. dr d theta d phi. So this is the differential volume for the spherical coordinate system. Okay, so you have to remember the ranges. The ranges of x, y, z, rho, r. Okay, are very important. Okay, and theta and phi is very important. Okay, so that's why you have to focus on this. Okay, so after completion of this, next we should go for the Gauss Law. So what is the Gauss Law? You should remember that. What is the Gauss Law? The Gauss Law is saying that the net electric flux leaving any closed surface, any enclosing surface is equal to the charge enclosed in that volume. Right? So whatever the charge is, suppose if you consider any closed surface, so from that closed surface, the net charge, the net flux coming out of the closed surface is equal to how much charge is put inside. It is called as the Gauss Law. Suppose if there is a charge outside, that considered volume, then the net electric flux will be 0. The net electric flux will be 0. So that is the point you have to understand. Suppose if it is not a closed surface, then Gauss Law is not applicable. Gauss law is not applicable. So that is the point you have to understand. So the Gauss law is only for the closed surface only. Okay, that closed considered symmetric surface is called as the Gaussian surface. Right? So this is the point you have to understand. Now suppose if you come to the Gauss law, so what is this Gauss law? Gauss law is saying that the net electric flux leaving any enclosing surface is equals to the total charge enclosed in that volume. The total charge enclosed in that volume. Okay, the net electric flux means what? Psi E total. Psi E total means net electric flux. That is equal to charge enclosed in the volume. So what is this? What is this closed integral d dot ds is representing? The closed integral d dot ds is representing Coulomb per meter square into meter square. Coulomb per meter square into meter square is called as the coulombs. Okay. Now I am calculating the total electric flux leaving that closed surface, right? So that's why I am naming this one as psi E total. Okay. So how much it is equal to psi E total? The psi E total must be equal to whatever the charge inside the closed surface. Okay. So this is closed integral d dot ds is equals to q. Okay, suppose if it is an open surface, this cannot be called as a Gauss law. Okay, that one is a closed, if it is an open surface, this cannot be called as Gauss law. Okay, this cannot be called as a Gauss law. So open surface integral d dot ds is equals to, it cannot be equals to q. It cannot be equals to q, and it cannot be equals to psi E total. There will be some electric flux, but it is not equal to psi E total. That is the point you have to understand. Okay, so this is called as the Gauss law in integral form. This is called as the Gauss law in integral form. Okay, suppose if I want to write the divergence, see, observe this. What is this actually? Closed integral d dot ds means the total effect. What is the effect? Effect is nothing but d dot ds is equals to d dot ds is nothing but the flux only. So the total flux within the surface. Okay. Suppose if I want to calculate the flux at that point. Okay. Suppose if I want to calculate the flux at that point, I have to represent this del dot d. Okay. Suppose if I want to calculate the flux at the cause, the strength at the cause, I have to represent this one as del dot d. Okay, so that's why it is called as the instantaneous value. Okay, so always remember the directional derivatives and directional integrations will be there in the vector calculus. Okay, always we use the integrations to find the total effects in the region. To find the total effect in the region. That is the point you have to understand. So when we use the differentiation, directional derivatives. So directional derivatives means what? Included the derivatives including the del operators, vector operators, right? So when we use the directional derivatives means to find the instantaneous value at any point, at any given point. So this is called as the Gauss law it is called as the Gauss law in the differential form. It is called as the Gauss law in the integral form. Okay, so it is used to find the total effects in a region. It is used to find the effect at that point, at any point. Okay, so this is called as the Gauss law. Okay, similar to that, if you come to the magnetic field, okay, so the Amperes law is defined. The Amperes law is defined. So what is the Amperes law? The Amperes law is saying that the total circulation in any closed loop, okay, the total circulation in any closed loop or any closed length is equal to the current crossing that surface. Suppose if there is any wire is there, okay, suppose if I consider at any point from the current carrying wire, okay, the total circulation on this line, suppose if I write a circle around this, okay, suppose if I draw a circle around this, okay, the total magnetic flux on this circle will be equal to the current crossing this circular area. Okay, so that is defined by the Amperes law. So this is represented by what? Closed integral h dot dl is equals to I crossing. Okay, so what is this closed line integral? It is the closed line integral. So what are these? Ampere per meter into meter. Amperes gives you current. But the important parameter here is you have to write a closed line integral. If it is an open line integral, then it cannot be the current. If it is an open line integral, it cannot be the current. Right? So you have to remember that. Right? So similarly, this is what the total current. It is the total current crossing that surface. But if I want to find the strength at the current only, suppose if I want to find the strength at this place only, on this line, on this current carrying length only, so I can represent this one as del cross H is equals to J. Okay, so what is this? Del is having a units of how much? Del is having a units of per meter, ampere per meter. So it will be having ampere per meter square. Always remember, del is having a units of how much? 1 per meter are the units. It is a very, very important thing you have to identify. Okay. If you observe this, what are the units of del? 1 per meter, Coulomb per meter square. Okay. So total Coulomb per meter cube. Coulomb per meter cube are the units of rho v. Similarly here, what is this? 1 per meter into ampere per meter. So finally, it is giving you ampere per meter square, right? So ampere per meter square are the units of the current density, right? So if I want to find the strength at a distance of r from the current carrying wire, I have to use this one. Suppose if I want to find the strength on this current, then I have to use this one. Okay, so this one will give you the instantaneous value on that current. So this one will give you the total effect in this region. Okay, so this is the Gauss law and Amperes law. So you go to the crash course videos and there is a detailed information about the Gauss law and the Amperes law. Okay, after completion after understanding this Gauss law and Amperes law, there is a very, very important theorems are, okay, so this is the divergence theorem and the Stokes theorem. Okay, it is also called as the Gauss divergence theorem. Okay, and the Stokes theorem. So what is the Gauss divergence theorem is saying, that is, see, already we have studied in the mathematics. Okay, here the Gauss law is already studied in the mathematics. Okay, so the Gauss law is applicable on the vector quantities only, but here we are relating that mathematics to our vector quantities. We know what are the vector quantities. These are the 4 vector quantities. So we are applying the whatever already defined the divergence theorem there. Okay, here on these vector quantities. Okay, already we have studied the divergence theorem in the mathematics. Now that divergence theorem was on the vector fields only. Now we are applying that divergence theorem on these vectors. So if I write this divergence theorem on these vectors, then what happens? So closed integral d dot ds is equals to what is this? Open closed surface integral. Closed surface integral gives you a volume integral of del dot d dv. Okay, volume integral of del dot d dv. So if you observe this, the double integral is formed into a triple integral. You have to write this. Okay, the double integral ds nothing but what? At a double integral. Surface integral is nothing but the double integral. Which kind of surface integral? It is a closed surface integral. Closed surface integral is forming a volume integral. Suppose if it is a open surface integral, you cannot write this one as a volume. You have to understand that always a closed surface can form volume, but not open surface, right? So that is the point you have to understand. Suppose if you come to the next theorem, it is called as the Stokes theorem. Okay, so it is relating the closed line integral to the open surface integral. Okay, closed line integral to the open surface integral. So closed line integral of h dot dl is equals to the open surface integral of del cross h dot ds. So observe this without mistake also. See, by mistake also you shouldn't write the closed integral here. By mistake also you should not remove this closed integral. Okay, so this is a closed integral. Here it is a closed integral. You should not remove this. If you are defining the divergence theorem or Gauss divergence theorem, you should not remove the closed integral. Okay, the closed surface integral is forming volume. Suppose if it is not a closed surface integral, then you cannot write this. Then you cannot write the Gauss divergence theorem for this. Suppose here, if this is not a closed line integral, you cannot apply the Stokes theorem. Okay, suppose if the line is closed only, there will be a open surface. If the line is closed means it is forming some surface. That surface is open surface. So here you should know that the closed line integral is forming open surface, right? So these are the very important formulas and expressions you should remember, and it is very valuable for you. I hope first of all, getting into the subject, you should know what are the causes of E field, what are the causes of H field, and what are the causes of electromagnetic fields. And after that, what are the remaining causes of the electric and magnetic field? That remaining causes are these one. Okay, so in this, these all are scalar quantities, but here it is a vector quantity, vector quantity, vector quantity, but here it is a scalar quantity. You should remember this, right? These all are the scalar quantities, Q, rho L, rho S, rho V, all scalar quantities. Remember that. And out of this, the current is a scalar quantity, but here IDL is a vector, K is a vector, J is also vector. These are all vector quantities, and del is also vector quantity, right? The curl of gradient is 0, and divergence of the curl is 0, and this is one more vector identity. You should remember this. Okay, so A is any general vector, and it can be represented in terms of the Cartesian, cylindrical, spherical coordinates. Okay, suppose if you want to find the divergence for the cylindrical or spherical, and you can use this. You know how to find the divergence curl gradient for the Cartesian coordinate system, but it is difficult to find the divergence curl for the cylindrical and spherical coordinate system. So that's why we should go for this generalized formulas. To know these generalized formulas, you should know this table first. If you are comfortable with this table, and they are very easy to find it. Okay, so already we know why we have to remember this means. See, there is a del dot D is there is del cross H is there. So that means del dot D, the D may be given in the Cartesian coordinate or cylindrical coordinate or spherical coordinates. Here H may be given in terms of the Cartesian coordinate, cylindrical coordinate, spherical coordinates. To find the current density or something else, to find the volume charge density or something else, you should remember this. Okay, so but in general, the del is operated only for the Cartesian coordinates, but here we are defining the del in other coordinate systems also. Okay, so that's why you should be very careful with the ranges of this x, y, z, rho, phi, z, r, theta, phi. Okay, and you have to focus on the divergence and Gauss theorem, and this will be helpful for the Maxwell's equations, for writing the Maxwell's equations, and these are very helpful. See, based on this you will get one question at least. Based on this you will get one question. Okay, if you are comfortable with this, you will get definitely 2 marks. Definitely 2 marks you will get minimum. Okay, if you are comfortable with this, you will get definitely 2 marks. Okay, suppose if it is engineering services examination, and it may be very helpful for you, because there are number of questions will be asked. So based on this you can identify, you can answer many of the questions. Okay, so this is a valuable information, so you have to remember this. Okay, so next, so in the previous slide, so we have seen how the okay, so come to the next slide. See here the electric field due to the point charge and the magnetic field due to the point current element. Okay, so we came to know due to the point charge the electric field is generated, and due to the point current element the magnetic field is generated. So what will be the amount of electric field okay, generated by the point charge. So here first of all you have to observe this, you have to identify the expressions of these two, okay, magnetic flux density and electric field intensity. Okay, see, observe this, here D is given, D means the electric flux density, it is equals to Q divided by 4 pi r square, okay, and the direction is AR direction. So always the magnetic flux density will be in the radially outward, okay, radially outward. Okay, so now similarly the magnetic field is defined by using the Biot-Savart's law. See, similar to this point charge, I am defining a point current element for the magnetic fields. Okay, for the electric fields we have defined the point charge here. Okay, here we have chosen the point current element for the magnetic fields. Okay, so due to the point charge, the electric flux density is equals to point charge divided by 4 pi r square into AR. So similarly for the magnetic fields, due to the point current element, we have defined the magnetic field intensity. Okay, magnetic field intensity is equals to IDL divided by 4 pi r square. So you have to observe the similarity here. So what is there in the numerator? Here the point charge means the cause of the electric field is there. But if you come to here, the cause of the magnetic field is there. So we can define the electric flux density is equals to cos divided by area. Cos divided by area, 4 pi r square means what? A spherical surface area, right? Similarly, the magnetic field intensity is equals to cos divided by area. Okay, the cos is ideal here. But here the electric field is in the direction of AR. Here the magnetic field will be in the direction. Observe this, it will be in the direction, here it is a dot product, here it is a cross product, you have to observe that. Okay, here the cross product. So because the ideal is a vector, okay, I cannot simply multiply vector into vector, I have to take the cross product of it. Okay, always remember the magnetic field deals with the cross products only. Okay, see, observe this, IDL cross AR. Okay, so what is the magnetic field direction now? Current direction cross radial direction. It is a current direction cross radial direction. That is what Biot-Savart's law is saying. Understand? So in the electric field, we have, first of all, we are defining the D. Okay? For the electric fields, we are defining D first. And next, for the magnetic fields, we are defining the H first. Okay, D is similar to H here. Okay, electric flux density is similar to the magnetic field intensity. Here, electric field intensity is similar to the magnetic flux density. Okay, you have to compare these two. Right? Similarly, what it is? Electric field intensity is defined by D by epsilon. Okay, so from this we can say that the electric field is dependent on the medium. Okay, E is inversely proportional to epsilon. That is the point you have to understand. E is inversely proportional to epsilon. Generally we will write D is equals to epsilon E. But E is dependent on epsilon. Not D is dependent on epsilon. That is the point you have to understand. Here B is equals to mu H. It is correct only. Okay, B is equals to mu H. So here the next defined term is electric field intensity. Here the next defined term is the magnetic flux density. Okay, here the next defined term is magnetic flux density. So this is the similarity you have to identify. So E is equals to Q divided by 4 pi epsilon r square. Already we have defined D here. Similarly we have defined H here. So B is equals to mu H. So IDL divided by 4 pi r square AR. Right? So we came to know that. So electric field is AR directed and magnetic field direction will be current direction cross radial direction. This is the point, very, very important, you have to understand. And next, from the Coulomb's law, what Coulomb has expressed means, the Coulomb has expressed the electric field intensity as force per the basic cause. Okay, force per the basic cause. So that's why E is equals to F by Q. It is from the Coulomb's law. Okay, so what are the units for electric field intensity? The units for electric field intensity are Newton per Coulomb. Okay, we know volts per meter, and next one is Newton per Coulomb. Similarly for the magnetic fields, the magnetic flux density is defined as force per the basic cause. Okay, magnetic flux density as force per the basic cause. Here also force per the basic cause. Here the cause is Q, here the cause is IDL, point current element. So the units are, we know Weber per meter square per B, okay, but by using the Lorentz law, we can write Newton per ampere meter, right? So from this Coulomb's law we can define the force equation. F is equals to Q1 Q2 divided by 4 pi epsilon R square AR. Okay, here from this we can write the F is equals to Q into V cross B, where V is equal to velocity of the charge in the magnetic field. So this is called as the Lorentz force equation. So we are talking about the point charges here. So due to the point charge, what will be the potential? The potential is equals to, what is meant by potential? Potential is nothing but the work done per unit charge. I am defining W, work done divided by the unit charge QU. I am defining this V is equals to Q divided by 4 pi epsilon R. Okay, so this is the potential due to the point charge. So cos divided by 4 pi epsilon R, this is the point you have to understand. Cos is what? For the voltage. Okay, the cos is the Q divided by 4 pi epsilon R. Similarly, for the magnetic fields, if it is the electric potential, right? So similarly, I am defining the magnetic potential here. Okay, the magnetic potential here is a vector potential. It is also called as vector magnetic potential. It is a scalar. Observe this. The electric potential is a scalar. V is equals to Q divided by 4 pi R. This is a scalar quantity, you must remember. And vector magnetic potential is a vector quantity. In the name itself, it is saying that it is a vector, but it is defined for magnetic fields. Okay, see, observe this. The electric potential is defined by Q divided by 4 pi epsilon R. Here the vector magnetic potential is defined by mu IDL divided by 4 pi R. You observe this. See, cos divided by 4 pi epsilon R means cos divided by, observe this, cos divided by 4 pi epsilon. I am writing 1 by 4 pi epsilon as K. Okay, if I write 1 by 4 pi epsilon as K, some constant, so V is equals to K into Q by R, right? Similarly, I am writing the vector magnetic potential A is equals to, here the constant as mu divided by 4 pi. Here mu divided by 4 pi as the constant. I can write A is equals to K into IDL by R, right? IDL by R. If you observe this, I am writing here K into Q divided by R, here V is equals to, right? Here also A bar is equals to K into IDL divided by R. So this is the point you have to understand. Okay. So here what is K here? For the electric fields, the K is 1 by 4 pi epsilon. For the magnetic field, the K is mu by 4 pi. It is dependent on the medium. Okay. So observe this. Here V is equals to, electric potential V is equals to some K into cos divided by R. Similarly, the vector magnetic potential for the magnetic fields is defined as K into cos divided by R. Right? Here K into cos divided by R. Here also K into cos divided by R. So you have to understand what is cos here. Okay? So this is the vector magnetic potential. Now what is the direction of this one? It is a scalar. So that's why there is no direction for this scalar voltage. Okay, so now but what it is, it is actually a vector quantity. So what will be the direction? The direction always will be current direction only. Ideal means what? The direction of DL will be always in the current direction only, right? So that's why the vector magnetic potential is a vector and it has a direction, current direction. That is the point you have to understand. Okay, electric potential is a scalar, vector magnetic potential is a vector, right? So here also there is one more definition for the potential in electric fields. It is equals to work done. Okay, work done, it is also represented as VAB is equals to integral E dot dl. Okay, integral E dot dl. Here don't put closed line integral here, it is a mistake. It should be open only. If you are making it as a closed, it making that, so it is a closed loop, so work done in a closed loop will be 0. So that's why don't write closed line integral here. Okay, here the work done is also is equals to integral here it is minus integral E dot dl, right? Here it is minus integral E dot dl. You have to understand this, right? So this is called as the potential. And similarly, if you observe this, the I am writing one more. See, observe this. It is a scalar potential in the electric field. Okay, so I am defining one more scalar potential in the magnetic field. Okay, one more scalar potential in the magnetic field. So I am defining the magnetic scalar potential. If you observe this, it is a electric scalar potential. Okay, but here what we have defined? We have defined vector magnetic potential. This is vector magnetic potential. But similarly to this, I am defining one more potential here. This is a vector scalar potential. I am writing this one as Vm, magnetic scalar potential, is equals to integral H dot dl. Right? This is not that much important, but you have to understand what is a scalar potential, what is a vector potential of the magnetic fields. Okay, there will be existing the scalar magnetic potential and there will be existing vector magnetic potential, but we have to more focus on the vector magnetic potential only. Okay, but here it is what? It is a vector into vector gives you a scalar only. Okay, so here the voltage is also called as the EMF. Here the Vm is also called as the MMF. Okay, it is also called as the MMF, and there is a relation between the electric field intensity and the voltage. So here the electric field intensity is defined as negative potential gradient. So E is equals to minus grad V. So from this relation we got this. So if you derivative this, you will get the E is equals to minus grad V expression. So this is the point you have to understand. Similarly, to get the magnetic field intensity from the MMF, so we have to use this relation. H is equals to gradient of Vm. But here there will not, here there will be minus sign, but here there will not be any minus sign. So you have to observe that. Okay, there will not be any minus sign. Okay, so in this, if you find this, observe this, if you find this VAB is equals to positive, if VAB is equals to positive, then we can say that the work is done by the external charge. Then the work is done by the charge. You have to understand that. Suppose if VAB is equals to negative, then we can say that the work is done by the field. Okay, so after finding this integral minus integral E dot dl is positive, then we can say that the work is done by the charge. If it is positive, then the work is done by the charge. If it is negative, then we can say that the work is done by the electric field. That is the point you have to understand. Okay, so similarly, I am defining the electric field intensity as minus grad V. Okay, similarly, I am writing the magnetic flux density as in terms of vector magnetic potential as B is equals to del cross A, and it is a very well known relation. You have to understand this. Okay, so similarly, as I am defining the electric field as the negative potential gradient, similarly I am defining the magnetic flux density as the curl of the vector magnetic potential. Okay, so this is the point you have to understand. Okay, so it is the MMF, it is the vector magnetic potential. Okay, it is a vector potential. So from these relations we came to understand that is the electric field is a function of what is proportional to 1 by r square. It is proportional to 1 by r square. Now what will be the potential? The potential is what? V is proportional to 1 by r. V is proportional to 1 by r. So this is the point you have to understand. Okay, the electric field is varying as 1 by r square, okay, but the electric potential is varying as 1 by r. And electric field is the vector quantity, electric field intensity is a vector quantity, electric potential is a scalar quantity. Okay, so these are the points you have to understand. Next one is very important thing is, if r is equals to constant in this, if r is equals to constant, what happens? V is also constant. If r is equals to constant, the voltage is also constant. Okay, so the r is equals to constant surfaces are called as the equipotential surfaces. Okay, so for the point charges, r is equals to constant surfaces are called as the equipotential surfaces. Okay, so if you now from the geometry we can say that if r is constant in the cylindrical coordinates, you will get concentric spheres. So the locus of r is equals to constant surfaces gives you the concentric spheres. That is the point you have to understand. So for the point charges, the equipotential surfaces are the concentric spheres. Okay, so suppose if there is a point charge here, so around the, if you assume concentric spheres, okay, all the concentric spheres are constant spheres only, okay, are constant spheres only, but r is constant, the voltage is also constant, so that's why all these concentric spheres are called as the equipotential surfaces. That is the point you have to remember. Okay, next, if it is completed, next come to this side, so it is due to the point charge, right? Now come to the electric field intensity due to the infinite length line charge. So already we know the electric field intensity, already we know the line charge is represented with rho L. What are the units of this rho L? The units of this rho L are Coulomb per meter. Okay, Coulomb per meter. So already we know, first of all we have to define the electric flux density as in this case. Okay, electric flux density is equals to cos divided by 2 pi r, rho L divided by 2 pi r. Similarly, for the magnetic fields, as the counterpart, if you observe this, the magnetic field due to infinite length current carrying wire. Always you have to compare the electric and magnetic field so that it will be easy to remember all the causes and effects. Okay, the causes and effects. So see what I am writing here, the electric field intensity due to infinite length line charge. Similarly, I am writing the magnetic field intensity due to infinite length current carrying wire. They are similar, right? It is infinite length, it is infinite length. If you observe this, it is a point charge, it is a point current element. Okay, where dl tends to 0 means it is also looking like a point already. We discussed in the previous slide. Okay. So d is equals to rho L divided by 2 pi rho a rho. Okay. So always the electric field or electric flux density will be in the radially outward direction. Okay. Similarly, the magnetic field. Suppose if in the electric field, if you are defining the electric field electric flux density, in the magnetic fields we are defining the magnetic field intensity. That is the point you have to understand. These two are similar to each other. Here also these two are similar to each other. Here the density is defined first, here the intensity is defined first. Okay, so here is equals to cos divided by 2 pi rho, where rho is the distance from the charge to the point. Here also cos, what is the cos? I divided by 2 pi rho, where rho is the distance from the current to the point. Okay, so what is this here rho? Rho means it is the radial direction. So what is radial direction? Radial direction is from the charge, from the line charge to the point. It is the direction showing. It is also, what is this? A phi. Okay, A phi. What is meant by A phi? Already you know from the spherical coordinates, A phi direction. Okay, suppose if the current is in AZ direction, then the magnetic field will be in A phi direction, like this. If the current is, let us suppose if the current is in this direction, AZ, okay, then the magnetic field will be in A phi direction. Okay, A phi direction, this is the point you have to understand. So how can I write this? A phi means, already you know, the magnetic field intensity, the magnetic field direction always will be current direction cross radial direction. If you observe this, you can easily write. Okay, so what is the current direction? I am assuming the current direction as Z direction. What is the radial direction? Radial direction is arrow direction. Radial direction is arrow. So AZ cross arrow gives you A phi. Okay, so this is the point. So from this what we can write? Electric field intensity. Electric field intensity is equal to d by epsilon. So I can write rho L divided by 2 pi epsilon rho arrow. Okay, always remember the electric field intensity, electric flux density are in the same direction. Okay, here also the magnetic field intensity and magnetic flux densities are in the same direction, but here one mu is multiplied here. Always observe this. Okay, so this is the point you have to identify. So from this, it is what? E is inversely proportional to, here E is inversely proportional to 1 by rho, here H is inversely proportional to 1 by rho. E is proportional to 1 by rho, here H is proportional to 1 by rho. Okay, so that is the point you have to understand. So after completion of this, now I have defined the magnetic field intensity due to the infinite length current carrying wire. Now if you come to the magnetic field due to the finite length current carrying wire. Okay, so if you come to the magnetic field intensity due to the finite length current carrying wire, then how can we define? Suppose if I am assuming a finite length current carrying wire which is from A to B, it is a finite length current carrying wire, then the analysis will be changed here. So the magnetic field intensity is equals to I divided by 4 pi rho sin alpha 1 plus sin alpha 2 into A pi. Here A pi again, A pi, I am writing A pi here. Okay, by assuming the current direction is in Z direction and the radial direction in arrow direction. Okay, radial direction, let us suppose this is rho. Okay, by assuming the current direction in AZ direction and radial direction in arrow direction, I am writing this. Suppose if the current is in other direction, so according to that you have to write this unit vector. Okay, always after writing this magnitude, you have to think about the direction of the magnetic field. Always the direction of the magnetic field will be current direction cross radial direction. Okay, so this is the point you have to understand. Next, I am defining the potential due to the infinite length line charge. Okay, already we have defined the electric field intensity. Okay, so from this electric field intensity we can get the potential by using this relation. By using this relation, V is equals to minus integral E dot dl. If you put this value here, you will get the potential due to the infinite length line charge. So if you observe this, you will get rho L divided by 2 pi epsilon ln of 1 by rho. Right? So from this, already you came to know that always the potential is a vector. Electric potential is a scalar quantity. Always the electric potential is a scalar quantity because electric field intensity is a vector and dl is also vector. The dot product of these two vectors will be a scalar quantity. So it is a scalar quantity. It is a scalar quantity. So from this we can say that V is proportional to ln of 1 by rho. Here E is proportional to 1 by rho. E is proportional to 1 by rho. So these are the points you have to identify. Always the electric field intensity for the infinite length line charge will be E proportional to 1 by rho and V proportional to ln of 1 by rho. This is the point you have to understand. Right? Suppose if you take rho is equals to constant surface. Suppose if there is a current carrying wire, we came to know that, so around this there will be the magnetic field will be existing around the current carrying wire. Okay, the current carrying wire. So if rho is equals to constant surface is taken for the cylindrical coordinates, so we can construct concentric cylinders. Okay, the locus of rho is equals to constant surfaces gives you the concentric cylinders. Okay, so for if rho is equals to constant, we came to know that V is equals to constant. If rho is equals to constant here, because these all are constants, so we can get the V is equals to constant. So from the geometry we came to know that rho is equals to constant surface is a concentric cylinders. Okay, so from rho is equals to constant here, then I will get equipotential surface. Okay, so from these two we can say that for the line charge the equipotential surfaces are concentric cylinders, or for the line charge the concentric cylinders are said to be equipotential surfaces. Right? So from this, so we can identify this. See, one more important thing here is while defining H for the finite length current carrying wire, so you have to take this I divided by 4 pi rho sin alpha 1 plus sin alpha 2. So here you have to remember one thing, where alpha 1 and alpha 2 are must be focused carefully. Okay, so alpha 1 is nothing but this one, alpha 2 is this one. So how can we identify alpha 1? So if the current is coming from this side, so the corresponding angle here at the point will be alpha 1. Okay, the remaining is alpha 2. Suppose if the current is coming in this direction, then it will become the angle made by this line at the point will be alpha 1. Suppose if the current is coming in this direction, this will be alpha 1. Right? So identifying the alpha 1 and alpha 2 are very important. Right? So now come to the electric field intensity due to the infinite sheet charge. So infinite sheet charge will be D is equals to rho s divided by 2 an, where an is the normal component from the sheet. Okay, normal component. Suppose if you take any sheet here, okay, suppose if you take any sheet, okay, if you take any sheet, then what will be the normal component? Suppose if I want to find the magnetic field intensity at any point, okay, the normal component will be in this direction. Okay, already this is a constant sheet. Okay, always the normal direction will be the direction which is crossing this surface. So this is the point you have to identify. So D is equals to rho s divided by 2 into an, where an is the normal component from the sheet charge to the point, that is the point you have to understand. Okay, this normal component may be in x direction or minus x direction, or plus or minus y direction, plus or minus z direction, like that. Okay, so similarly here I have defined the electric field intensity as, we know E is equals to d by epsilon, so you can write that rho s divided by 2 epsilon. Here the direction is same here. Okay, similarly the magnetic field intensity due to the infinite sheet current, it is defined as K, right? So K will be having ampere per meter. Here rho s will be having the units Coulomb per meter square. That is the point you have to understand, right? So units must be matched. Here Coulomb per meter square, here ampere per meter. Okay, the units must be matched here. D is having Coulomb per meter square, rho s is also having Coulomb per meter square. If you observe this, the magnetic field intensity due to the infinite sheet current, K, is defined as H is equals to, here first of all what I have defined, D. Similarly, the H is defined in the magnetic field first. Okay, so H is defined for the magnetic field first. So H is equals to K by 2 cross An. Okay, K by 2 cross An. Here only just multiplication, here the cross product is taken here. Okay, so how can we define? The electric flux density is defined as cos divided by 2. What is the cos here? Rho s divided by 2 into An. Similarly, the H field is equals to cos divided by 2 cross An. Here cos divided by 2 into An, here cos divided by 2 into 2 cross An. Okay, cos divided by 2 cross An. Similarly, we have defined the magnetic flux density mu is equals to mu into H. Okay, so mu into this part K by 2 cross An. Okay, if you observe this very clearly, okay, what's happening here? The electric field intensity, electric flux density and electric field intensity, here the magnetic field intensity and the magnetic flux intensity only they are dependent only on the causes, but not dependent on the distances. Okay, but not dependent on the distances, how much distance the point of interest is existing. It is not at all dependent on the distances, it is only dependent on the causes only. If the cause is constant, definitely it will be constant. So the D is constant, here also the E is constant, here also the H is constant, B is also constant, because we are considering these causes rho s and K are constants. So that means they are independent of distances. So what are these? Electric field intensity, electric flux density or electric field intensity, magnetic field intensity, magnetic flux density. These are independent of distances. If you come to here, they are dependent on distances. They are dependent on distances. Here also they are dependent on distances. They are dependent on distances. But if you come here, they are independent of distances. So that's why these all are called as uniform fields. That means they will be same everywhere. Either electric field or a magnetic field, they will be same everywhere, and the electric flux lines here are parallel to each other. Here also the magnetic flux lines here are parallel to each other. Okay, so this is the thing you have to identify when you come to the uniform fields. So due to the infinite sheet charge, you will get the uniform fields. So this is the thing you have to identify this. So if you come to the next thing, so the very important concept here, the Poisson's and Laplacian equations. So generally these Poisson's and Laplacian equations are morely concentrated on the electric fields only. They are not that much important for the magnetic fields, but even though I have written here, so observe this. So here del square V is equals to minus rho V by epsilon. Here rho V is called as the volume charge density. Here rho V is called as the volume charge density. Okay, suppose if you consider the free space means the charge free region, then del square V becomes 0. This is called as the Laplacian equations. Okay, and this Laplacian equations is very helpful for finding the voltages or a charge also. Okay, voltage or charge also. So why it is useful means, if you come to this, see, if you want to find the electric field intensity due to the point charge, okay, or electric potential due to the point charge, there are some equations are there here. Okay, due to the electric field, it is the electric field intensity, it is the electric potential. Similarly, if you want to calculate the voltage without giving the point charge, how can you calculate? Okay, suppose if you want to find the voltage of any surface, okay, but the point charge or electric field intensity will not be given, but only one equation will be given. Okay, so how can you identify? So first of all, it has to give the scalar surface, right? So from this we can get the charge or electric field intensity from this. Okay, so that's why, so del square V is equals to minus rho V by epsilon, we have to use this. Okay, so from this we can find the charge, because charge density is there, right? So one scalar function will be given, voltage function will be given. So from that voltage, if you want to find the charge, then you can easily find by using the Poisson's equations. You can easily find the Poisson's equation. Okay, so if you take the charge free region, then rho V is equals to 0, then we can use this relation del square V is equals to 0. This is called as the Laplacian equations. So similar to that, the Laplacian equation for the magnetic fields will be del square of A is equals to minus mu into J. See, observe this. Del square of electric potential is equals to minus rho V by epsilon. Del square of A is equals to minus mu into J. So here is the material constant, epsilon is there. Here also material constant mu is there. Okay. So here is the volume charge density is there. Volume charge density rho V is there. Here the current charge density is there. Here the scalar potential, here the vector magnetic potential. Okay, similar to this, we have to compare this, right? And we have to focus on the Poisson's equations, and the questions are coming from this Poisson's equation. Suppose if you want to find the charge from the charge by using some voltage function, we have to use the Laplacian and Poisson's equation. Okay, so you go to that concept and you solve 2-3 problems over there, and it will be very helpful for you. Okay, without using the electric field intensity something, so we can easily get the charge. Okay, so like this we can identify. Now, so these are the next boundary conditions. So if you come to the boundary conditions, There are two types of boundary conditions, electric field boundary conditions and magnetic field boundary conditions. So while considering the boundary conditions here, okay, so there are two kinds of interfaces we have to observe here. Suppose if the two medium, why we are using boundary conditions means, suppose if you know the field in the one medium, okay, to calculate the field in the other medium, so we have to use definitely the boundary conditions. Okay, so you have to, the fields must satisfy the boundary. So then only we can happily use this boundary conditions to find the fields in the other medium. Okay, so if you observe this, if you consider the first one, dielectric interface, that means first medium is dielectric, next medium is also dielectric, then these are the first boundary conditions of the electric field. Okay, so dN1 is equals to dN2. What is dN1, dN2? The normal component of the electric flux densities are equal. Here dN2 minus dN1 is equals to rho s. Okay, so here these are the two conditions here for the electric flux densities. If you observe this, dN1 is equals to dN2 means what? In the word form I can say that the normal component of the electric flux densities are continuous. The normal component of the electric flux densities are continuous if there is no sheet charge at the boundary. Okay, the normal component of the electric flux densities are discontinuous by an amount rho s if there is a sheet at the boundary. If there is a sheet charge at the boundary, that is the point you have to understand there. So while he is asking about the field in other medium by giving the field in the another medium, okay, so we have to focus whether the sheet charge is there at the boundary or not. If the sheet charge is there, we have to use this relation by using the normal component of the electric flux densities. Okay, and one more important thing is the tangential component of the electric field in the first medium and second medium are same. That means the tangential components of the electric field intensities are continuous always. Okay, they are continuous always means equal always. Okay, similarly if you go to the magnetic boundary conditions, okay, they are exact opposite to this. Here the magnetic flux densities, the normal component of the magnetic flux densities are continuous always. Okay, similarly we can write, and they are the tangential component of the magnetic field intensities are continuous if there is no sheet current. If there is a sheet current and they are discontinuous by amount k bar, that current, okay, that sheet current, and they are discontinuous by an amount k. What is k? K is the sheet current placed at the boundary. See, observe this, in the text books he might have given HT1 minus HT2 into AN2. Okay, some normal component will be given, it is equals to k. Okay, you can also that way or you can also this way, and no need to confuse with this. So it is better to use this one. Okay, always HT2 minus HT1 is equals to k. You have to focus on the directions there, right? Similarly, if you use the boundary conditions for the dielectric and conductor interface, okay, here the tangential component of the electric field intensities are 0. Okay, for the conductor, the tangential component of the electric fields are 0, because if it is a conductor, there is no accumulation of the charge. Always the electrons will be, the charged particles will be moving in the conductor, so there is no chance to forming the electric field. So that's why the electric field along the conducting surface will be 0. So that's why E tangential is 0. Okay, E tangential is 0, and the normal component of the electric flux densities is equal to the sheet charge obtained on the conductor. The sheet charge obtained on the conductor, and dN is equals to rho s. Where dN is equals to rho s, always this electric field will be away from the conductor. Always the electric field will be away from the conductor, pointing outward the sheet, pointing outward the conductor. Okay, so these are the things. So you have to identify, and they are very, very important. And while studying the EMT, you have to compare both the electric and magnetic fields, so that everything will be clear for you. Okay, so I hope you are following well, and this session is very, very important. Okay, so each and every final revision part of each and every video is very important, and we guarantee that you will get not less than 80% of the marks if you clearly observe this. Okay, so thank you, and thank you very much.